Hello guys, welcome back, PK here. So in this video, we're going to be evaluating this interesting and challenging integral. So the question is, we need to evaluate this integral from 0 to infinity. Then we have z times ln z over z cubed plus 1 and dz. So for this question, we will see that later, but we need to take a look at this integral of now c and then z times ln z squared over z cubed plus 1 and dz. And in this case, we can specify your c. C has to be now the keyhole contour. Keyhole contour, and at the same time, we can visualize this using maybe epsilon and the r. Then we need to work on the branch cut too. Branch cut for the log along the positive x-axis. So we can visualize this. Okay, so we are working on the branch cut that will be looking like this. So say this is now your center, and then we are working on the circle that is looking maybe like this, in this direction. Okay, then we have the r, which has to be the radius. Then we are working on the branch cut, so it should be looking like in this. Okay. And then at the same time, this would be some kind of like little circle, right? Little circle, and we'll be using this epsilon as the radius of this little circle, which should be positive, but I'll keep this as small as possible. And then for the big one, the radius r, that is also the positive number, but I'll keep this as big as possible. Okay, so this is the basic visualization. So we're working on the keyhole contour, and then we'll be working on now the branch cut for the log along the positive x-axis, right? So that's why this has to be the circle with the radius of the r. And then for the little one, we can call this as the circle with the radius of the epsilon. Okay, based on this setup, then we should have now the 3 poles, right? Those 3 poles is going to be one of them e to the power of now pi I over 3. And then the next one is -1. Then the last one is e to the power of negative pi I over 3. And then they are the roots. Roots of z cubed plus 1. But then again, make sure we're working on the branch cut. So that's why we'll see this later, but we should be using e to the power of 5 over 3 pi I. We'll check this. But we need this because of the branch cut that we're actually working on, right? But then again, before we move on, we need to talk about why we have ln square of the z instead of just the regular ln z. We can talk about it using the branch cut, right? So on the branch cut, from your epsilon e to the r part, right? This part is represented as ln of the z. But then again, from r to epsilon, this part is going to be now ln of z plus 2 pi I. That's why we need this ln square of the z, right? Okay, then using this, what we need to calculate is this. We have integral from epsilon to r, right? And then we have now z times ln square of the z over z cubed plus 1 and then dz. And then plus now from r to epsilon, then we have z times, and then we have ln z plus 2 pi I now square over z cubed plus 1 and dz. Okay, this is what we need to calculate. But then again, we can combine these two, right? We can combine these 2 integrals into one integral from epsilon to r. Then we should have now, pulling the z out, then we have, let me make a bracket, ln square of the z minus, and we have ln z plus 2 pi I square. Close your bracket, and we have z cubed plus 1 on your denominator, and of course we have dz, right? Okay, then we can represent this integral as now integral from epsilon to r. Okay, then we have z, and I'll be making a bracket too. So we have -4 pi I ln of z, now plus 4 pi square. Close your bracket. Denominator is still at z cubed plus 1, then we have d now z. So that's why we can break this integral into the 2 integrals. One of them should be -4 pi I. Integral from epsilon to r, then we have z times ln of z over z cubed plus 1 dz. And then plus 4 pi squared integral from epsilon to r. Then we have only z over z cubed plus 1 and then dz, right? Okay, this is the one. Now what we need to do is we need to think about what will happen to the integral for CR and C epsilon. CR was the circle of the radius R, and C epsilon has to be the circle of the radius epsilon. So let's talk about what will happen to the integral to CR, right? Okay, first of all, integral over the CR, right? So integral over CR. Okay, this will become 0 if your radius R is going to infinity. We can easily check this out. So the absolute value of integral based on your CR, right? Then we have z times ln square of the z over z cubed plus 1 and dz. Okay, so this one is now the less than equal to 2 pi r times ln square of the r over now r cubed minus 1, right? Then at the same time, this will go to 0 if your r is going to infinity. So that checks out. And then number 2, what happened to the integral over c epsilon? So second integral over c epsilon. Okay, this will also go to 0 if you're keeping epsilon to go to 0. Also, we can easily check this out, the absolute value of integral of now the c epsilon. Z times ln square z over z cubed plus 1 dz. Right. This has to be now then less than equal to, okay, 2 pi of the epsilon times epsilon ln square of the epsilon over now, it is 1 minus epsilon cubed, right? This will go to 0 if you're keeping your epsilon going to now 0. So these two checks out, right? Now we have everything for the setup, and then we can work on the integral and then make a calculation, right? So for the simplicity, I'll be calling this fz as now z times ln square of the z over z cubed plus 1. I'll be using this. Okay, so this is your f of z, right? Z times ln square z over z cubed plus 1. From the beginning, we talked about those 3 poles, right? That means we can work on your integral using residues. Okay, so based on this, now putting all together that we have already, then you're working on now negative 4 pi I integral from 0 to infinity. Then we have z ln of z over z cubed plus 1 dz plus 4 pi square of integral from 0 to infinity. Then we have only z over z cubed plus 1 dz. Okay. Okay, so from this, what I'm going to do is I'll be calling this as just the I, right? Okay, if you call this as the I, then what we need to work on is going to be the same as 2 pi I times now the residue of f of e to the power of pi I over 3. And then plus residue of now f of negative 1 plus now the residue of f of e to the power of negative pi I over 3. Okay, this is what we just need to work on, right? Okay, then this is going to be the same thing as now I plus now pi I of integral from 0 to infinity. Then we have z over z cubed plus 1 and dz, right? And then what we can rewrite this is now negative 1. This is the same thing as negative 1 over 2 of the residue of f and e to the power of pi I over 3. And then plus residue of f and negative 1 plus now the residue of f and e to the power of negative pi I over 3. Okay. Okay, in this case, what we can talk about is this I and integral from 0 to infinity, z over z cubed plus 1 dz. These two are the real numbers. But then again, pi I times this integral is a pure imaginary number. So that's why for this question, what we need to check is now your I has to be just equal to negative 1 over 2 times only the real part of this whole bracket part. And that is what we need to calculate. That means we don't need to calculate the integral from 0 to infinity z over z cubed plus 1 dz. We don't need to calculate that because of that reason. Okay, now let's make a calculation for this, right? So first of all, let me factor this z cubed plus 1 out. This is the same thing as now z plus 1 times z minus e to the power of pi I over 3 times z minus e to the power of negative pi I over 3. Okay. Right, so that's why we set your f of z as z times ln squared z over z cubed plus 1, right? So that is why for that part, we can rewrite this as now your f of z. That is now equal to z times ln squared of the z over this expression. Z plus 1 times z minus e to the power of pi I over 3 times z minus e to the power of negative pi I over 3. Okay, this is your expression for the f of z, right? Now we need to calculate the residues. Residues of f of e to the power of pi I over 3, residue of f of negative 1, and then the residue of f of e to the power of negative pi I over 3. Let's start with this first residue. Residue of f of e to the power of pi I over 3. So we are now working on the residue of f of e to the power of pi I over 3. Okay, so in this case, we have the ln, right? So noticing how ln of e to the power of pi I over 3. This is the same thing as just a pi I over 3. Okay, so using this, your expression has to be now the z, that is e to the power of pi I over 3. Then multiply by pi I over 3 now square. That divided by, okay, so e to the power of pi I over 3 plus 1 times e to the power of pi I over 3 minus e to the power of negative pi I over 3. Okay, so if you calculate this, then it's the same thing as now pi squared. So it has to be negative pi squared over 9 times this whole thing, the rest of it, which is e to the power of pi I over 3. That divided by, now, e to the power of pi I over 3 plus 1 times e to the power of pi I over 3 minus e to the power of negative pi I over 3. Okay. So we need to focus on this part, right? Of course, we'll be calculating the real part of this later. But yeah, this is the expression for the first residue, the residue of f of e to the power of pi I over 3. Okay, then we can move on to talk about this residue of f of e to the power of negative pi I over 3. From the beginning, we talked about how we can use e to the power of 5 over 3 pi I because of the choice of the branch cut that we show in the beginning. So we'll be using that. Okay, so now we're working on the residue of f of e to the power of negative pi I over 3, right? So the residue of f of e to the power of negative pi I over 3. Okay, so for this question, what we can notice is now ln of e to the power of negative pi I over 3, right? So for this one, we can represent this as 2 pi I minus pi I over 3. That's the same thing as 5 over 3 pi I, as we said at the beginning, right? So that's why if you work on the expression, then it has to be now e to the power of negative pi I over 3 times now 5 over 3 pi I now square, right? That divided by e to the power of negative pi I over 3 plus 1. Okay, then that multiplied by now, so this part is e to the power of negative pi I over 3. Now minus e to the power of positive pi I over 3. Okay, so if you calculate this, then what we have is now square of that is equal to negative 25 over 9 pi square. Multiplied by all of these terms all together. E to the power of negative pi I over 3 over e to the power of negative pi over pi times I over 3 plus 1 times e to the power of negative pi I over 3 minus e to the power of pi I over 3. This entire term. Okay. Now, notice what we have on this. There's only one more part, residue of f of negative 1, right? Residue of f of negative 1 is going to be the easy part. So, now we are working on residue of f and negative 1. So, that part. This part is going to be easy. This is now equal to negative 1 now times pi I now square. That divided by negative 1 and then minus e to the power of pi I over 3. Okay, times negative 1 minus e to the power of negative pi I over 3. Okay, so if you make the calculation for this, then you will end up with pi square over 3. So we have everything, right? So like I said, we are only getting negative 1 over 2 times only the real part of this, right? Okay, as we know, we are only interested in negative 1 over 2 times real part of this, right? We got all of them, residue of this and residue of that and residue of f of negative 1. So basically what we need to talk about is then what should be the real part of this remaining part, right? This part has to be the same between residue of f of e to the power of pi I over 3 and the residue of f of e to the power of negative pi I over 3. So we need to talk about what has to be the real part of this so that we can multiply that real part to those terms for the residues. For that part, we can use this Euler's identity. So talk about e to the power of pi I over 3. So we can represent this as cosine of pi over 3 plus I times sine of pi over 3. Okay, so that's why this has to be now 1 over 2 plus square root 3 over 2i, right? So that's why using this, and then if you calculate this, then we can easily say the value of this part for both of your residue of f of e to the power of pi I over 3, and then the residue of f of e to the power of negative pi I over 3. This will easily turn out to be 1 over 6 minus 1 over 2 radical 3i. So that's why 1 over 6 has to be the real part of this expression. Now we're almost done. So the residue of f of e to the power of pi I over 3, it had negative pi square over 9 as the real part. You need to multiply 1 over 6 to it to have negative pi square over 54. Residue of f of e to the power of negative pi I over 3, we had this. Negative now 25 over 9 pi square. You need to multiply 1 over 6 to it, right? Then it has to be negative 25 pi square over now 54. And then the residue of f and negative 1, you only have pi square over 3. All we need to do is add them up. So pi square over 3 is the same thing as now 18 pi square over 54. So that's why if you add them up, negative 26 plus 18, that is negative 8 pi square over 54. But then again, we need to multiply negative 1 over 2 to the real part of this. That turns out to be negative 8 pi square over 54. We need to multiply negative 1 over 2 to it. So that's why if you calculate this, and the final answer for this question is negative, negative become positive. And then we have now, then that's equal to now 4 pi square over 54, which is going to be then 2 pi square over now 27. So this is the final answer for this question. 2 pi square over 27 was the answer. Okay, pretty interesting but challenging integral using contour integration method. So I'll be back with more videos for more questions like this sometime soon.